Okay, morning. Do you hear me? Okay, can you guys hear me?
Yes, yes, okay.
Yeah, thank you. Because I'm now at school, so yesterday I found I experienced some internet issues in terms of Wi-Fi. So I don't know whether or not it will be okay. It seems that the problem set to be solved, but please be patient. If that is the case, please PM me right through WhatsApp or the phone, right, to get to know the situation. If you found the connection problem, okay, being undesirable. This is. I hope finger crossed, right, for all of us, no problem. Because in the last lesson is Form 4, right? I spent quite some time on that, on tackling the issues about internet. Now, while you're waiting, you may know I have finished the topic on chemical equilibrium, right? So any more questions about that? Now, before we proceed to the last chapter, that is textbook 5. Now, while we're waiting, could you please go to your bookshelf and get textbook 5. This is the last topic for paper 1. Do you have it? Now, don't worry if you don't have it. Now, you may not, you do not find any hard copy of the book. Now, please check your Google Classroom. Please check your Google Classroom. We have got one message, right, about this. We call that patterns in chemical world. Okay, under the category patterns in chemical world. Now, just make sure that you have found this. Right, I should locate where it is. It's on here. Sorry, I'm still marking the work that yesterday, and sorry to say that these 2 weeks I'm quite busy about the DSCs, but to the best of I can do is to keep on posting those work to the Google Classroom, but sadly I may not have the returning of the work may be delayed. Sorry about that. So this is the one. Have you all got that? Textbook 5. So today we have got 2 chapters, right? You have got 2 chapters, but today we just finish. We just have a start of chapter unit 41. It is a periodic trends in elements and compounds. Can you see that? While for the last chapter, very last chapter, it is the transition metals. Can you see that? Transition metals. Do you find it? So this is the 2. So today we would have 41 first. Please download it. Now we will start the lesson right away. After 1 minute, I'll give you 1 minute to get yourself prepared for the lesson, and we'll start right away. I find one of you absent. Could you please help locate who he is? Is it one of them absent? Let me check. Oh, all of you are here. Is it 22 in this class? I forgot. 22 or 23? 梁家傑 Anyone who find梁家傑? Okay, now I will start the lesson. Anyway, we'll start the lesson right away. Now, the chapter for this, because I need to charge the notebook, so you may not see my face. Sorry about that. But I would also, I will also continue my lesson, right? So the periodic trends in elements in the compounds. I can hear some. Yep. 梁家傑 finally here. Finally reached the classroom. 梁家傑, are you here? Right. So go to the Google Classroom and download textbook 5, topic 5, or you simply use your textbook at home. We will start the lesson right away. Now, today, periodic trends, periodic patterns. It is. Some of you may think that, Mr. Jin, is it just a recap of what we have learned? To a certain extent, yes. Because some of them, some of the topics were covered in the past. If, for example, bonding and structure. Now we visit some similar topic here. What else? And you may find acid and alkalides. Also, you may get redox reactions inside, right? All those. And you may also heard of something like rates of reactions. Okay, so mainly this. So mainly these four questions that topic that that it gives you a very good foundations, right, of these topic. For paper 1, so mainly appear in the last it being the last topic, we have got about 1 or 2 MCs only, and 1 long questions. But that long questions only comprises 3 or 4 marks. So it really depends on your strategy or for the preparation of the DSE chemistry. Now, some of you may simply skip it, okay? But to me or to us, in case you want to have a recap of those 4 important topics, now you use this foundation knowledge to read it. You read through this, you may find that we also have a synergic effect, okay, by incorporating that 2 topics, that 2 knowledge together. So this is another way, right, for you to get yourself prepared well for this chapter. This is paper 1, not so many marks, and you may see it, but it also gives you a good foundation of that. So once you revisit all those topics, I would usually jump back to the foundation knowledge to help you better understand these parts. Okay, do you know my strategy? So this is unit 41. Now we visit the periodic table. So we would not only focus on the main groups, elements, transition metals. Okay. Now number 3 and number 4, lanthanides and actinides. No need. no need for DSE. And you may see the word, maybe we focus mainly on the chemical property similarity in terms of diana group, right? But we seldom you talk about across a period. Now, in these two chapters, we would focus on these, okay, across a period. What happens about those chemical elements in terms of the period. But of course, just take a look on one period doesn't help. That you may see the word periodic. So why do we say that as a periodic? Now, why would we say called periodic table periodic? Do you know? Something like repeating, right? Periodic. So periodic in this sense will mean something that will repeat itself, right? After passing through that one period. Okay, so of course, later on that you will know that it is more or less related to the number of outermost shell electrons, and you try to offer explanation based on this, right? So this is what we understand in periodic pattern. So remember, today we focus on this, right? Take a look on across the period. Okay, so transition metals, and when you compare with main group, it is said to be less reactive. So you may find that because of the relatively more stable chemical property, so we will find that metals being quite useful. Now, no need to mention that something about the high strength of the metallic bond when you compare this with paper group 1, group 2, and group 3. Okay, relatively, they have a stronger metallic bond. So we will cover that later. I will offer you some explanation. Okay, stronger. All of you, please mark it down. Stronger metallic bond when you compared with group 1 and group 2 main group metals. Okay, while for the naphthenites and actinides, why can't we have a full coverage of that? Because we need not get to know some about the radioactive elements. Okay, so that radioactive elements, for those who have got interest in it, you may get to know more in physics, or maybe in university chemistry and or physics. We will talk about how we will make use of the radioactive elements to be used as one of the applications, right, in our human life, such as like nuclear power station, right, or nuclear weapons, etc., or even to understand something about the universe, right? They would to make use of that. So we would mainly focus on, instead we will mainly focus on the periodicity. So remember, the periodicity means the recurrence of the same pattern across a period. Okay, across the period, which means that starting from today, we focus on from left to right, but not from top to bottom. Okay, so this is what we would like to revisit that one. So period 2 and period 3, the difference is the number of what occupied electron shells. But for if we talk about the group, we will talk about the difference being number of outermost shell electrons, right? Just recall your memory about that. So first, just recall your memory about the periodic pattern. In Form 3, what have you heard? Form 3, just name one or two. Lei Cheng, do you know? Could you please name one? The periodic pattern that is observed while you learn chemistry in Form 3.
The atomic radius goes up across the period.
Metallic radius.
Atomic radius.
Atomic radius. Atomic radius, what happened across the period?
Becomes
climbing up,
bigger.
Decrease.
Increase.
Or increase. Increases across the period. Agree? All of you agree? Now it is decreased, right? It decreases. Okay, what else? Lâm Thành Hon. Do you have any memory about the periodic patterns that you know in Form 3? While you talk about why periodic table is set as periodic.
Melting point increase to group 4 and decrease. So.
Yeah, melting point increase from group 1
to group 4
to group 4, climbing up, and the pattern
and then
will drop.
Gradually decrease.
Okay, they will drop from group 4 to 0, but you say that gradual decrease, right? So it's time to check if that is the case. Gradual decrease, right? You mentioned the gradual decrease. So 3, can I have Deng Ho Jun? Anyone do you know? Do you still remember that pattern?
Hi.
Yes. Form 3. Recall your memory in Form 3. What do you know?
係咪首先一開始係 metal 再變 metalloid，最後係 not metal，即係由左至右。
Okay, the changing is the pattern is from metals to non-metal, right? In between metal and non-metal, what is that? We call that
transition metal.
Transition metal. Non-metal. So here is transition metal, is it? So take a look on this period and period 3. Do we have any transition metals? Can we tell B and Si is not transition metal? We call that semi-metal. Or we call that metalloid. Okay? Metalloid. 半金屬. So the behavior would be in between metals and non-metals in a certain extent. Remember that the electrical conductivity is not just in the middle, but between metal and non-metal, but they will have a very slight electrical conductivity, right? If you talk about the electrical conductivity of semi-metals. So remember, it's not transition metal. Transition metal is a metal. Okay, but semi-metal is not a metal. So we focus on this. Okay, boron and silicon. Okay, is that clear? So we'll talk about that too. It is different. So you may find you may heard of something more, right, about the periodic pattern. How about reactivity? Do you still remember about the reactivity? Any periodic pattern that is observed from group 1 to group 0? Thẩm Quang Nhật. Thẩm Quang Nhật. Any periodic pattern that observe about reactivity? Which elements are said to be quite reactive? That is mainly on group 1 and group 7. Okay. How about less reactive one? It is in between, right? Mainly group 4 and group 0. It is said to be unreactive. Okay. Now, so if you want to talk about these, if you describe the reactivity, we would mention it in terms of number of outermost shell electrons, right? But for these, right, we will have some other way to explain. Okay, you will know it. We visit it later. So just take a record on period 2 and period 3. I try to put these two as example. For the elements mainly on the left hand side, you may see there are the similarities in terms of appearance, right? Now, most of them, they are said to be silvery solid. Now, and while you go to the middle, now you may find the two, boron and silicon, being semi-metal. How about the one on the left right hand side? You may find non-metals with various color. It's dull, not silvery. Some of them solid, or gases, right? For liquid, it's rare to find. It's just bromine, which is liquid at room temperature and pressure. Now, if you revisit something about Form 4 chemistry, bonding and structure, here comes the periodic pattern, okay, in terms of the bonding and structure. Take a look on that. Do you still remember that? Yeah. So it's time to revisit that. So if you want to take a look on that bonding and structure, so you may find the general pattern from period 2 to period 3. So that type of pattern is also repetitive, right? Giant metallic structure on the left hand side, while for simple molecular structure on the right hand side. Now in group 4, some of them group 3, you may find these three. Can you see that? They are said to be having a giant covalent structure, while the particles responsible, right, to connect the bonding is different. Do you still recall your memory, right? While for giant metallic structure, it is the positive metal ion surrounded by the delocalized electrons. Remember, bonding structure is usually referring to electrostatic. Do you still remember that term? Electrostatic force of attraction. Now, because of that, electrostatic must be referring to the intrinsic attraction between opposite charge. So whenever you talk about bonding, please refer to what is positive and what is negative when you describe this bonding environment. Okay. Now, for this, we may find lithium, beryllium, sodium, magnesium, aluminium. There are 5 metals having a giant metallic structure, while the particles should be the vibrating metal ions and free moving, we call it mobile electrostatic delocalized electrons. While for giant covalent structure, so the particles to be involved is just atoms. Can you see that? Atoms, underline the term atoms. So the atoms, they are held together by strong covalent bond. Because of that, you may find these 3 substances have a relatively high melting point, because you need quite a large amount of heat in order to overcome the attraction forces between those particles. While for the one on the right hand side, so you may find they are simple molecular structure. We focus on the intermolecular force. Okay, intermolecular force. So when the force amount, the molecules will be considered, okay, except group 0. So group 0 is a very special example because they are monoatomic. We still have van der Waals force, okay, but you talk about the monoatomic molecules or simply atoms, right? So you simply skip that. If you don't want to get confused, even though you write down molecules, I still give you marks. But that type of molecules, the nature of it is just monoatomic. While that van der Waals force, there are so many types of van der Waals force, okay? So what type of van der Waals force are we mentioning? Dispersion, dipole, or what? Do you remember this one? Do you remember?
首先唔係 dipole 先啦。
Yeah.
敦頓都好似唔係啦。 剩低個
咁即係咩啊？咁即係咩啊 ？It's neither London force nor 大埔 attraction.
forget it。
應該即係得 hydrogen
So what
bond
else?
得返
What else? What else can it be? So indeed, London force, it is just the same as dispersion force. It's also just the same as instantaneous dipole induced dipole attraction. They are just the same. Okay, they are just the same. All right, can you get what I mean, right? So these three, they are the same. Well, dipole, we talk about polar substance. Okay, so this is different. So we visit all those giant metal structure with a diagram. Just to remember that is Mg2 plus. Those the localized electrons come from what? Where? Outermost shell electrons. Okay, so giant covalent structure between atoms. It is rather strong, while the molecular structure, so depending on the structure, right? We would like to revisit that too, right? Because it is, you may not find it so common in Form 4. While you learn in Form 4, so simple molecular structure P4. Now this is structure. While for SH, it is a crown sulfur structure. All of you, please mark it down. Crown, the one, the king, right? So you have got the crown above the head. We call it crown. While for this one is the tetrahedral structure of P4. Each P atom, they are connected by 3 single bonds with the neighboring phosphorus atom. So by doing so, each phosphorus atom inside P4 molecule will be octet. Okay, while does this sulfur being group 6, okay, sulfur atom being group 6, it is connected by 2 single covalent bonds with neighboring atoms within the molecules. So by doing so, sulfur atoms will also attain octets inside the molecule. Just to remember that. Of course, because of the different structure of that you may have different forms, right? We call it allotropes of sulfur, just like rhombic sulfur and monoclinic sulfur. But don't worry about that because we seldom talk too much about that. Now we focus on this. Now this one is highly needed, right? You need to memorize this about the patterns in chemical world. From lithium, beryllium, boron, now just like last time, you separate them in terms of bonding and structure. So we have got 3 groups. Okay, while for 3 groups, it will more or less help by explaining in terms of what? The bonding structure. So please put a boundary here to tell you here, period 2 and period 3. Can you follow? Okay, so you may find period 2 and period 3. Now he seems like a heel structure, right? Very similar. Can you see that? Very similar. Climbing up, down, climbing up, down. While those on the right hand side is this giant structure. But of course, if you serve further separately, we call that metallic and covalent, respectively. While the simple molecular structure, we mainly focus on the later half, on the right-hand side of the periodic table. Can you see that? Now, Mr. Chin, do you mean that we need to memorize the exact temperature, the melting point temperature? No, no need. But you have to memorize the pattern. Okay, the climbing up the hill, drop down, especially where on these parts. Maybe some of you may find it quite hard to memorize this. So first of all, state the pattern. The melting point increase from group 1 to group 4, sharp decrease from group 4 to group 5, and then relatively low from group 5 to group 0. So you may find these two telling you that it decreased, but it's not a gradual decrease. Now, just like this, a rapid drop, okay? A rapid drop, it's not gradual decrease. But for the first 4 elements in the group, in the main group, they would have a general increase. Okay, all those can be explained in terms of bonding and structure. So, do you still remember that? Now, in order to get to know more about this, we need to separate the argument in between 3 of them. Now, first of all, how will you get approach to the essay type question? For example, if I ask you, are the variation of melting point in period 2 or period 3? Now, mainly period 3 is frequently asked period 3. So how will you get approach to the problem? So you may first of all separate into 3 groups, okay, and try to compare these 4 and these 4, 2 different groups, one big group, giant structure. Of course, melting point is relatively higher. Simple structure, melting point being relatively lower. Give me explanation. And then you go into detail to talk about within those elements having the same structure. For example, that 3, where is a variation in melting point? While you skip that, you go to these 4 and try to tell me what is the variation in the melting point among the 4, and with explanation. And then later on, you give us an overall conclusion to tell us that we have got a climbing up and down. Can you get my point? So remember, the way to answer that problem is not one by one. Remember, from a more macroscopic viewpoint to very tiny, comparing one by one approach. Of course, you need not compare one by one. Instead, you use the pattern. You use the trend to explain. Can you get my point? So this is what we usually do. Now, no need to compare one by one. What do I mean by that? You may not need to compare melting point between sodium and magnesium, sodium and aluminum, sodium and silicon, sodium and phosphorus, right? No. Instead, we would separate into groups and compare among the 3, compare among the 4, like this. Do you understand? You understand our approach. So by doing so, the type of comparison will be more neat in terms of in front of the reader, the examiner. So you may find these. Can you see that? Now, I separate it into 3 in order to explain. But within those elements having the same structure, we still have further elaboration. Do you understand? So we come to this metallic and this. Please change it now. Please change it now. This attractive forces. What is that? Attractive forces. Change it to what? Now, could you please do it one by one? Now, loss of this one. The strong covalent bond. What for this? Weak van der Waals force among the molecules. Yes, that is correct. This is correct. What for this? You change a little bit. Okay. You understand? Now, this. We come to this. Do you need to have a more coverage on that? Now, we call your memory about that. Melting point between sodium, magnesium, and aluminum, period 3. Sorry to say that I need to reply some of the message about DSE invigilation. Just wait for me. Sorry. Now, sorry about that. So the strength of metallic bond is affected by, now, just recall your memory about this, right? When you compare this with what Mr. Chin have said, any difference between them? It is something about negative, right? It is something about size and also the charge of metal ions. Okay, all of you please mark it down. It's something about positive. Now this one, what is that? We call it packing. We call it packing. But of course, in DSE, we focus on these two now because it will allow you to have a easier comparison. Because that two is fair enough for you. But for this, it may be new to you. Right? We talk about packing. So in if you study material chemistry as your elective, okay, even though most of the Hong Kong candidates didn't take it, just 4 to 5%, as I remember, 4 to 5% of the candidates will take industrial chem, while most of us would take, including us, we will take industrial chem and analytical chem. But you have got a further coverage on this, the packing. So you may refer it in the later chapter. Now, so we would recall your memory about all those. What is that? So we would mention it like this. All of you, please copy it down if you still haven't memorized it. Right? Didn't recall your memory. Number of outermost shells, electrons that would affect the strength of metallic bond. It's something negative. While something positive is the size of metal cations and the charge of metal ions. They would affect our strength of metallic bond. Do you still remember? So the one red is referring to something negative, while the one I mark it blue, it is positive, right? So number of outermost shell increases, the strength of metallic bond increase. That's it. Okay, can you get my point? So how about the blue one? We have got, you want to make it increase, what should we consider about this? The charge should be high, but the size of metal ion should be small. Do you still remember that? Skipped. Easy to skip. Skip. 記得嘛呢啲? And one of the pattern, if you talk about the periodic pattern, so you may find this sentence, right? The size of metal ion decreases from sodium to aluminium. Can you see that? So they will have a greater metallic bond, stronger metallic bond between the metal ions and the localized electrons. So as well as third way is about the degree of compactness. Okay, how close packed it is. So from sodium or aluminum is more close packed. So altogether, we will talk about metallic bond. The strength of it increases. Now, don't worry about too much about this part, degree of compactness of the packet. You may use the similar principle in molecular structure as well. Do you remember organic chemistry? We also consider this part, right? So mainly melting point, we focus on packing together with other elements which would affect our strength of metallic bond. Now, so you may find this, right? The packing. So it is also commonly seen. Now, while you mention it as melting point. Now, but for boiling point, where we seldom mention it, only melting point, we talk about it. Now, very similar, right, to molecules. Because for melting to liquid to boiling from liquid to gas, right, we are nearly overcoming those attraction forces between those randomly moving particles. So we seldom talk about it as a regular packing, right? So no need to mention about packing. Just remember. So for those who want to get to know more about how come the atomic radius of a metal decreases, okay, you need to across the period. It's not only group 1 to group 3, but also across the period. Also have such a trend. It decreases across the period. You may refer to chemistry lengths. Now, it is something about the electrostatic attraction between the nucleus and outermost shell electrons. So this one being positive, this one is negative. So you may find that very confusing while you compare this with metallic bond. Now, recording the memory about metallic bond, the definition is the attraction between the metal ions and out the localized electrons, right? But for this part, you are mentioning as the nucleus. Attraction between nucleus and outermost shell electrons is different. The difference is on here. Can you see that? This is the difference. Not metal ions. It's not metal ion. If you talk about this, these two as a matching, we talk about it as metallic bond. Just remember. But if you talk about this, what is that? We call that a effective nuclear charge. So we would call it as a net nuclear attraction. So why would we say that it is a net nuclear attraction? Because you will say that net is not just attraction, but also repulsion. So if you want to talk about attraction, we call it nuclear charge. It is the attraction between nucleus being positive and the outermost shell electrons being negative, right? But at the same time, you may find it as shielding. Shielding, it is, we call that an electron repulsion. Shielding effect. Okay, so in between the inner shells, we have got electrons. They would have a intrinsic repulsion. Why? All those, they carry the same charge. They are negative. They are negatively charged. So they will repel each other. So we repel it with the outermost shell electrons. So between inner shell and outer shell. Can you see that? So that will reduce the nuclear attraction. So it is just a competition between the two. So I would like to show you in terms of graphics. You will get to know what I mean. Easier. The nucleus, we've got so many shells. We have got electrons. So if you want to talk about the first one, nuclear charge, you talk about this. This is nuclear charge. It's a type of attraction. But if you want to talk about repulsion, we refer to this. So the net, with considering the black one and the red one, we've got the overall, right? We've got the overall, there should be attraction, right? It does make sense. Otherwise, the ultimate electrons is said to be escape. Okay, that electrons will fly to the infinite distance between the nucleus. So, can you get my point? So, of course, it will have a net attraction. But if you want to compare these three elements, we are comparing how large the difference is then of the net nuclear attraction. We got the effective nuclear charge. Can you get my point? So, in order to explain that, of course, you may refer to the fact that both, when I across the period, there will be more electrons added, right? At the same time, we have got more protons added. Can you get my point? We have got that too, both increase, which means that nuclear charge increase, shielding effect also increase. But the extent of the increase of shielding effect, it will be less. Why? Because you are now adding the electrons in the same outermost shell only. So the shielding effect, because of that too, the electron repulsion in between, not in between, within the same outermost shell will be less than the one between different shells. What do I mean by that? Is that these two, that type of shielding is stronger, while these two within the same shell, it is weaker. Can you get my point? So, of course, what we say it just like earning money, right? Earning money $10, but earning money just $1. Can you get my point? So you may see Mr. Chin, they will add the tick here, right? That too, we have got two ticks. Well, we have got that one tick across the period. Can you get my point? That extent of increase is less, but the nuclear charge extent of increase is more. So altogether, they will have an increase in nuclear charge. Can you get my point? So what is the overall? Overall is that we have got an increase in effective nuclear charge. So resulting in the atomic radius decreases across the period. Why? Because the outermost shell electrons, they are said to be pulled in towards the nucleus more strongly. Do you understand? Do you understand? Okay. So the second part I would like to share with you because it's rather complicated. I'll just give you a guidance in reading. It's about the pattern. It's about the closed back structure in material chem. If you want to study more about that, you will know it later. So why we say that packing will also affect the string of metallic bond? It's because of the difference in packing. They're quite different packing structure. One of them we call that closed packing. One of them we call that an open packing. Open, which means the packing efficiency is less. Quite less, it's about 74%. But you want to talk about it as all those we call it closed packing, it will be risen up to 80 something packing efficiency. 80 something percent packing efficiency. So we will call that closed pack structure, closed packing. While for open packing is just 70 something. Now, why we say so? Now, for closed pack, it seems like having the stacking of oranges. Do you still remember? You have got orange to put it together, just like you give an offering to an ancestor, right? You may have that 4 oranges putting like this way. Can you get what I mean? 拜祖先啊，拜神啊. So you may have got 4 oranges, you place it like this way, right? It is a very traditional way of having a very close back structure. So what does it mean by that? Among the same layer, what I mean is these. This is another layer, right? The other three circles in the bottom layer, they will pack it quite close. Instead of this, if you want to put that four oranges in the same level, same layer, you may find the packing efficiency is rather less efficient, right? We call that open packing. It's rather open, especially while you have got one orange here and a third layer on the same level. It's rather open, right? Why you say so? Because the space in between is rather large. Can you get my point? While for this, it's rather close. And because of that, we have got two patterns. One is we have got ABA layer. The third layer repeat the layer A. What we have got ABC layer as well. So because of that, we have got two different patterns. We call that hexagonal close back or face hexagonal close back. We have got this AB layer, as well as cubic close packing CCP, in which the packing pattern is different. For this one, AB layer, which means first layer 1, layer 3, layer 5, layer 7, odd number layer is the same position. The atoms, metal atoms are packed in the same position. While ABC layer, which means that we've got the three different way of placing it. So we call it ABC. While layer 4 repeats layer 1 and repeat it accordingly. But if you want to talk about this one, it is rather open packed, less close pack. We call that body sample cubic. So you may find that one, as I said before. We have got the base having a square base, but once I place another ball in the second layer, that you may find you have got more space in between. So it's rather open, less packed. Okay, less packed. Just remember, less packed. So you may know this later. Now, before we end up the lecture today, we would focus on this class practice. You're comparing the melting point between them. Period 3, sulfur, chlorine, and argon. You have to memorize these two, especially. Do you still remember? P4SXCl2 and AR, argon being monoatomic. While the van der Waals force among them, we have got that order. While that order, it corresponds to the difference in molecular size. Also in this pattern, SX being greater than P4, being greater than Cl2, being greater than AR. All of it, please mark it down. So because of this, what would affect? It is affect the strength of van der Waals force among them. So it will affect its melting point and boiling point. Of course, mainly we talk about boiling point because the attraction force between them is rather weak. So with that, the room temperature, we have got enough heat to overcome those the intermolecular force between them. Any questions so far? Now, all those you have heard it before. Now, in the last 10 minutes, take a look on that. Just finish them. Now, the graph below shows the melting point on consecutive elements in the second and the third period. Oh, that may be, you have to find out the boundary, right? Which cuts between second and third period. Do you find it? Identify the elements represented by Y, justify answer B and C. Please spend some time on it. Do it now. Can you find out the cutoff to show the period 2 and period 3? And what is that? Usually we have got the melting point being the highest. So usually which group does it in second and third period for all those? But we have got this one having the highest melting point. What can you expect? What do you expect to be?
Group 4.
Yes, group 4. But if you say that period second third period is highly likely as third period, group 4. So can you identify F?
Silicon.
Yep, it's silicon. So justify your answer is silicon. So how will you answer that? How will you answer that? You may need to get to know the explanation in terms of bonding structure. How will you say so? What structure are you? Some please. How will you answer that? Some keywords should appear. What keywords should be having?
Giant covalent structure.
Yes, giant covalent structure. What else? The bonding.
Atoms are bonded with strong covalent bond.
Okay, the atoms are held strongly by covalent bond. What else? How you relate to the highest melting point among them? Yes.
可唔可以講多次？
咁你講咗 bonding 嘅 structure 嘛，跟住你點樣楞住個 melting point 咧 ？How you relate this to melting?
A lot of energy is required to break the bond.
Lots of energy in terms of heat, right? In terms of heat is needed to overcome the forces between them, which relates to the very high melting point. Okay, so fair enough. Fair enough. We have got that. Now remember, if you write down identify, you simply write down silicon or SI. But if I change this term to name, you can only write down silicon, the full name, but not symbol. B, explain the difference in melting point between elements represented by C and D. Now, because of that, I know that silicon, you do it backward. Okay, you're doing it backward. This fluorine, right? So you are going to find it. That one corresponding. Fluorine, neon, sodium, magnesium, aluminum, silicon, and then last two, what is that? Phosphorus, sulfur, right? Just to remember. So recall your memory. For easier comparison, C and D. C and D here. Explain the difference in melting point between them. So you need not mention something about packing because you need to memorize. You need to memorize the difference in packing. Now, indeed, if you study material chem, you need to, but it's optional, don't need. So we mainly focus on the difference in strength in metallic bond when you compare C and D. Can you get my point? So go back to something basic. Go back to something basic. So can I hear some keywords from you? Some keywords. What are they in common in terms of bonding structure?
Both of them have giant metallic structure.
Yep, and then
metallic bonds exist between the metal ions and the C of the localized electrons.
Now, this is very important. This is, we call it a general overview. Okay, so we have got metallic bond, also metallic bond between metal. What you say? So metallic ions and the localized electrons. What are they sharing in common? Is this? But the next sentence should be make a difference. So compare C and D, right? So, could you please continue about the comparison between them?
Each magnesium atom has 2 outermost shell electrons, while each atom of sodium has only 1 outermost shell electrons.
Magnesium versus sodium, right? 2 versus 1. You compare with negative. How about positive?
Ion of magnesium has a charge of +2, while that of sodium has a charge of +1.
Charge +2 versus charge +1. What else? Just recall your memory about the
size of
yes, good size.
Ions.
Yes, size of ions. Size of ions. Which one is larger? Which is smaller?
Sodium is larger. Magnesium is smaller.
All together. So with considering of all 3 factors, what is it?
Stronger metallic bonds exist between magnesium ion and the sea of delocalized electrons.
So when you compare with a metallic bond in what? D? Is it D? D being stronger than that in C. Okay? Can you get my point? So this is you need to make a comparison. First of all, on the left-hand side, you mentioned about negative and something about positive. You mentioned on the right-hand side. And all together, we are going to compare the strength of metallic bond being stronger compared to before we arrive at the answer of melting point. Now, of course, somebody would love to put one more item that is also okay. It's about the energy needed to overcome the attraction force between them. Okay, because this is a bridging point between melting point and the strength of bonding, right? Good, thank you. How about C? Identify the difference. Identify element represented by B. Why is it melting point is so low, very special? They mentioned something about neon, right? Neon. Lastly, for neon, is neon. Can you tell me, recall our memory about bonding structure in neon? What structure are we having? Hello, Wang Long. Hey. Wait, we've got 1 minute left. Hurry up. Wang Long, hurry. Can I have Jeremy?
Neon has a monoatomic structure and which is simple molecular structure.
Yep.
By weak van der Waals forces. It is dispersion forces. Therefore, little heat is required to overcome the attraction forces. Therefore, the melting point of neon is so low.
Good. This dispersion force, or you mention it as a van der Waals force between an amount of molecules. Rather, we have got little heat needed to overcome the attraction forces, so which accounts for the very low melting point.
Oh,
Do you still remember those? Do you find this one a very meaningful topic, which seems like wrapping what you have learned it in 2 years chemistry? Do you realize, right? It seems like wrapping. Recall your memory. Go back to the one in Form 4, right? To get to know this. So we will continue on electrical conductivity and something new, right? In the later part. Okay. Do you find it? So in short, today we mentioned something about bonding and periodic pattern. And in terms of period 2 and period 3, and we mentioned the difference in structure, difference bonding between them. What else? We mentioned the variation and melting point between them. There will be more to come. So what do you think about this? Easy, difficult, or what? Manageable, right? Seems like recalling memory, isn't it? Seems like recalling memory. Of course, some more challenging topics can be found in the packing as well as the effective nuclear charge, right? That 2 concepts. Don't worry, if you finally choose not to study material chemistry for the topic of packing, you need not mention. You need not memorize. Okay, is that clear? So just go back to the concept of bonding. First of all, bonding structure, what structure they're having, what bonding they are having, the bonding between them, what are the particles involved, and lastly, comparison. So this is what I would like to share with you today. Any questions so far? Now, if not, I will just stop it here. See you next time. Bye-bye. Now I need to do EDS invitation.
Bye.
Bye-bye.
拜拜，先生。
拜拜拜拜。
拜拜，先生。